Let's go ahead and get started. Like I said, we're in chapter 7.6, work applications, work problems and their applications. And we talked last time just a little bit to kind of introduce you guys to the concept of units. Work is equal to force times distance. So depending on whether you're in the metric system or the English standard system, in the metric system, force is measured in newtons. The standard unit of length is meters. So in the metric system, the Newton meter, also known as the joule, is the standard unit for work. In the English system, force times distance, force is measured in pounds. Your standard unit of length is the foot. So you're talking about foot-pounds for the standard unit of length. So these are the units you've got to convert to meters and convert to feet and so forth and so on to be able to get your work and stuff. And so we talked a little bit about that last time and about the idea of, work is all about this concept of lift. And so I'm getting into this a little bit later on when I'm doing these actual problems, but the way I'm going to set these problems up for you guys, especially towards the end of these problems with the pump problems and stuff, I'm going to be lifting things, and when I'm focusing on lift, the traditional y-axis is the natural axis to integrate with respect to. So you're going to see a lot of integrating with respect to y problems and stuff. So, but you're going to see calculus in these problems very quickly. Okay? So, first off, I did these two problems for you guys last time because they were straight kind of problems here. I've got a 60 kilogram object I wanted you to lift for 3 meters. Problem with kilograms measures mass, so you got to multiply it by gravity. So you need things you need to know. The metric system, gravity is 9.8 meters per second squared. So 60 times 9.8 gave me 5,588 newtons. That was my force, times a distance of 3 meters, gave me 1,767 newton meters or joules of work. So I had to take my kilograms, my mass, multiply it by gravity to get the force, then multiply that times the distance that I happen to lift it. English system, a little bit nicer in terms of way to use it. It's just not very nice in terms of converting factors over. Work is equal to force times distance. I give you a 60-pound object, and I want you to lift it 5 feet in the air. It's pretty much 60 pounds times 5 feet, 300 foot-pounds. So in terms of the math, the English system is a little easier to go because we just give you the units you need. Metric system, they're going to make you jump through hoops, and they give you kilo mass. You're going to multiply it times gravity to get the force. Then you got to take all that good stuff and then multiply it times the distance you want to convert over. But then later on, we'll do problems like this. So let's take a look at this problem here. This is a somewhat reality problem here. Jessica McClure became famous at the age of 18 months after falling into a well in the backyard of her home in Texas on October 14th, 1987. Between that day and October 16th, rescue workers worked 58 hours to free, quote-unquote, baby Jessica from an 8-inch well, wide well casing 22 feet below ground. If the rescuer, so we'll get to the math in a second, but let me give you the gist of this thing here. I just picked something out of history. This is when CNN became very popular on cable news networks, 24-hour news networks, because this actually went worldwide. And it was a baby, 18 months old, and she was in Texas. And one thing they got in Texas is oil. And typically what they do is they drill for oil, and they put a very small well casing, like you said, about 8 inches wide, straight down, drill down to the oil, and they have these little oil pumps. But after they pump all the oil out of it, they just pull their rigging up and go on to the next place, and they cover up the well casing with a piece of steel, about an inch thick piece of steel, just stick it on the ground on top of the hole. They don't fill it in or anything like that. They just kind of cover up the hole and move on to the next area where they believe is oil out, and then drill another hole down there. Well, what happened was that piece of steel that was covering up the hole in these folks' backyard, somebody happened to, it moved by wind or something or other, pushed it away, and the hole was visible. And there's a little girl just running along in the backyard, 18 months old, just running along, and all of a sudden, she's gone. And had to go find baby Jessica. She actually fell 22 feet down, straight down into the ground, because, you know, it's a straight down pipe that they were dealing, and she got herself wedged, because she would have gone a lot further than that, but her arms got wedged and stuff like that. So for you guys that don't know about the old baby Jessica and CNN, First Cable News Network, I did this little thing for you guys, just to give you guys a little episode of, kind of give you a visual of what was actually going on here. You don't hear the little, all it is music. You just get to read the little stuff here, but fell into a well October 14th. It was 22 feet deep and 8 inches wide. It was televised on CNN, and these are the folks that actually did it. So, and Jessica was trapped in the well for 58 hours, and they finally got her out. She was rescued, like I said, almost 58 hours later, and that's a picture of her right there. That's what she looked like getting out of a well. Okay? But now she's married with 2 children. She's actually doing very well. They had a, before the days of GoFundMe page, they had a big old effort to go fund her, and she actually received, when she turned the age of 21, and got a nice little endowment from all the things that she was into and stuff like that. So, I don't need that mess. Okay. All right, so back to our problem. Now, the reality of the famous baby Jessica problem was this. The kid was 22 feet down in the well down here, okay? So I want to give you a little history on exactly what they did. How do you go and get a baby out of a well who's stuck in a well 22 feet down? Well, she's wedged in there with her feet, so she's not like sitting at the bottom and stuff like that. So what they did was the rescuers, they pulled a bunch of guys that basically are miners and stuff like that. And what they did was they came over here and they dug a hole, a mine shaft hole, and they came in and dug down, and some poor sap had to go in there into this little hole, and they came in from below her and grabbed her this way and then carried her out over here, is actually what they did. How they ended up getting the baby out of the actual well casing, stuff like that. But that's actually too much work for us to do, so let's take a look at how I came up with this problem. All right, so this now it's no longer history and reality, it's just how I would have done the problem. All right, so if a rescue worker pulled Jessica from the well using a rope that weighed 3 pounds per foot, okay, so you got the rescuer right here, and he's using a rope 3 pounds per foot, and assuming Jessica weighed 25 pounds, how much work is done in pulling Jessica out of the well? So, I would have just chunked her rope down here and said, grab it, and then we would have yanked her up there. So, here's the deal. So the first thing you got to do when you do a problem is, number one, pay attention to units, because this is physics now. And units are the most important to let you know. What am I dealing with? 22 feet down, the kid weighs 25 pounds. This is an English Standard System. You with me so far? The next thing you got to do is you got to draw a coordinate axis on this thing. So I'm going to draw myself a little coordinate axis. I'm going to put my coordinate axis, it's up to you, but I'm going to put mine at the bottom. So here is 0. Here's where my worker is at. It's up here at the mark of 22 feet up in the air. From here is where my little baby Jessica is located at. Okay? And now this guy, my little worker, construction worker, is going to throw down this. Now let's think about this for a second. Now let's analyze this thing. This cable down here to the baby so we can pull it out. Now we're not going to wrap around the baby's neck. We hope to get around her waist or something or other. Pull it out. Otherwise we got a real problem here. So we're going to pull the baby out. But here's the real deal. The work to get the baby out of the well is equal to 2 things. It's going to be the work on the rope or cable that we're using, okay? So we'll call this work total, work T here. Work total. The work for the total system is going to be work on the rope plus the work on the baby. Because there's 2 things going on here. You got to get the baby out of the well. That's actually easy math. Because here's the deal. To get the work of the baby, work is equal to force times distance. How much does this kid weigh? She's an 18-month-old kid. How much she weigh? 25 pounds. Times Where do we want to lift this kid to? We want to lift her from the bottom well to the top well so she can get out of the well. 22 feet. Does that make sense? So, grabbing my handy-dandy calculator here, that pretty much is a straightforward math. 25 times 22. That's the easy part. So the work to get the baby out of the well was 550 what? Foot-pounds. Does that make sense? The real calculus comes in. It's not the baby, it's the rope. So let's understand from a calculus perspective. I drop 22 feet of rope down here. Now what does this rope weigh? The rope weighs, what is it here? It is 3 pounds per foot. We got a nice cable, and that's a nice thick metal piece of cable here. This darn thing weighs 3 pounds per foot. So let's talk about it at the beginning. 3 pounds per foot, we got to drop 22 feet of cable down to get to the kid. That's going to be 66 pounds. Does that make sense? 66 pounds of rope cable that I had to drop down to her. But now, what are we going to do? We're going to lift it out of the well. So as you start to lift this cable up, the cable is actually going to start changing. Does that make sense? It's going to start weighing less and less on how much we have to handle. So 66 pounds down here, halfway up, now it's only weighing 33 pounds. And then as I get to the top and pulling it over here to the side, eventually, you understand, it's changing. There's where your calculus comes in at. So here's a formula you're going to use a lot of. That formula is equal to work is equal to the sum of the delta force times the distance. This is my work problem written from a Riemann sum perspective. Work is equal to force times distance. But if I focus on the change in the force and multiply that distance and sum all those things up, that'll be equal to work. There's another formula, and I'll show that to you here while I'm talking about formulas. Work is also equal to the sum. Maybe your force is constant and your distances change, times the change in distance. So these are two different kinds of formulas where you put the change on the force or change on the distance, but when you sum those changes up, that actually gives you the work. And you know where I'm headed with this stuff. Integral calculus. Summation turns into integration. That delta stuff turns into that d stuff derivative. Our formula we're going to be using for this problem is this guy here. Okay? So now I've got my coordinate axis. What I'm going to do is I'm going to analyze a little piece, in this case, piece of the rope. I'm going to come over here and I'm going to take myself, and now I'm making a little slice. This is a little delta y slice. You with me? I'm going to analyze that little section of rope. That little section has a particular change in force. That little section is the change in force is equal to what? Now, how much does that section of rope weigh? How much does that little section of rope weigh? It weighs what? 3 pounds per foot. So that's 3, I'm going to use my units, 3 pounds per foot times how much little rope do we have here? I just have a delta y, which is in feet, of rope. Look at your units. Analyze your units. What happens to the feet? What's pounds per foot times foot turn into? Pounds. So, and what is force measured in? Pounds. This is change in force, which would be 3 delta y, and that would officially be in pounds. That's what this little section of rope is. You with me? So work is equal to the sum of that little section of work, that change in force, is 3 delta y times the distance I have to lift that little section of rope. Now, this is on the y-axis. Work is all about lift, and the natural axis to integrate with respect to would be the y-axis and showing that lift. So here's my y-axis right here. And this, I could have made the cut down here, up here, anywhere along this section of rope. I just made it somewhere here in the middle. It's at an arbitrary y level that I made that cut. What is the distance I've got to lift that little section of rope to? What's the distance of it? Distance is top minus bottom or right minus left. I keep reiterating these formulas with you guys. So in this case, where's my target? The target is to get the baby and the rope up here to the point of 22. Does that make sense? So what is my distance? Top minus bottom, 22 minus y. Does that make sense? Now, convert this to integral calculus. Very important. So work, and this is the work on the rope. So put a little subscript R on this thing. The work on the rope. What does summation turn into? Integration. 3 is a constant, leave it alone. Your function is 22 minus y. And what does the delta y going to turn into? dy. And all you need to do now is figure out your bounds. What are my bounds going to be? We want to remove all the rope out of the well. Does that make sense? So what am I going to integrate from and to? Again, it depends on where you put that coordinate axis. So drawing coordinate axis is paramount to do any kind of these problems. I put my coordinate axis at the bottom where the baby was located at. And that, so my distance would be from 0 to 22. Does that make sense? Did I lose you guys anywhere? Now, all I got to do is integrate to get the work on the rope. 3 is a constant, leave it alone. The integrate that goes out front, integral of 22 with respect to y would be 22y. Minus integral of y would be y squared over 2, evaluated from 0 to 22. According to the fundamental theorem of calculus, you plug in top minus plug in bottom. This will be 3 times 22 times 22 minus 22 squared over 2 minus 3 times plug in bottom, plug in 0. You pretty much get 0. That goes away. So this is 3 times 22 times 22 minus 22 squared divided by 2, just putting it exactly on my calculator, minus 0. And I get 726, and that would be its work, its foot-pounds. So, therefore, to answer your question here, to get the work total on this problem, you've got to take the work on the rope plus the work on the baby. The work on the rope was 726 foot-pounds, plus the work on the baby, that was a straight lift and jerk concept here of 550 foot-pounds, which makes the answer how much? 1,276 foot-pounds. That is the answer to my problem. Again, not quite reality of what happened back in 1987, but if I'm going to get the baby out of the well, the only thing I could think of, because I'm not digging that big a hole, I'm just going to go ahead and chunk a rope down there to her. Does that make sense? But that's what they had to do. But I got another question for you, a physics question. Let's say, for example, in this problem, I'm focusing on the rope problem here. I want to do, basically, in this first part, I want to lift the baby out of the well. So I'm going to integrate the whole thing. Listen to my words, because they're going to come back and haunt you with this stuff. This section is not that bad, but practice, 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 and this is classic physics application. Pay attention to units. Let's say, instead of lifting the baby the entire way up the well, and remember, you integrate over what you remove, I want to be a sadist, and I want to lift the baby halfway up the well and just let her dangle there for a while and see what happens, just for fun. What would I have to integrate over? Think about it now. 0 to 22, that would be lifting the baby entirely out of the well. But this time, I just want to lift the baby halfway up the well for meanness. What would I integrate? Well, I got two options. Is it 0 to 11 or 11 to 22? That's the question. One of them right, one of them's wrong. You integrate over what you want to remove. I'm removing the rope. When I'm lifting it from the top, I remove the rope at the bottom. Does that make sense? So what I would have integrated from 0 to 11. Does that make sense? Questions? That concept, remember it, because it'll come back when I start doing fluid problems and stuff like that. When you want to integrate half the stuff out, you want to integrate over the part that gets removed. That'll be important. Okay? Did I lose you guys anywhere? Well, here's another very similar kind of a problem. Let's do this one. A 2-pound bucket is lifted from the top of a 20-foot tall building by a cable at a constant speed. The cable weighs 0.1 pounds per foot. Part A, how much work is needed to lift the bucket and the rope from the ground to the top of the building? Part B, how much rope is needed to lift the bucket and the rope from the ground halfway up the building from 0 to 10, and then how much work is needed to lift the bucket and the rope the rest of the way to the top of the building from 10 to 20. Now, I want you to look at this stuff because people think, oh, this is just math. All I got to do is divide this mess by 2, and that's not exactly how it works. So the first thing let's do is, all right, so we got a nice little construction problem here. And so part A, we've got down here, we got ourselves a 2-pound bucket, 2 pounds on the bucket there. And we got the cable. And the cable is actually weighing in at 0.1 pounds per foot. We want to lift both the bucket and the cable up the building. And this guy is on the second floor, top of the second floor, somewhere or other. He needs to lift this thing 20 feet. Does that make sense? And we want to calculate how much work is involved. Now, the first thing I always told you guys is this. Redraw your picture because you got to put a coordinate axis on this thing. Traditionally, I like to put the coordinate axis at the bottom of whatever scenario I'm looking at. And that's usually the case. There's a few examples that I won't put it at the bottom, but in this example, I'm going to put it at the bottom. And the reason why I put it at the bottom, it makes all my numbers positive because, again, work is about lift, and the natural axis to integrate with respect to is the y-axis. So when your zero's at the bottom, all your numbers are positive, and it's easier to explain to other people. So always put the coordinate axis at the bottom. So here's my coordinate axis. So down here is where the bucket is located at. I put it at 0. So our target is up here at 20 feet. Okay? So here's my guy basically pulling my rope with my little bucket down here at the bottom. Okay? Again, same problem as in the baby Jessica problem. To get the work total, you've got to take the work on the bucket this time plus the work on the rope. There's 2 things going on here. One of them is typically really simple. Which one's going to be the simple math? The work on the bucket. The work on the bucket, because the bucket is constant, it doesn't matter at what level you put it, it's still, it's force times distance. The force is constant. The distance is constant. The force was what? What was the bucket weigh? 2 pounds. How far we want to lift it? 20 feet. Again, the English system here, that's a classic 40 foot-pounds. Does that make sense? That's the easy one. Where the calculus comes in at is the work on the rope. The work on the rope, you need that special summation formula. The work on the rope is the sum of that delta force times that distance that you want to do the lifting. It's force times distance, but written as a summation. Now, to analyze the little delta force, what you're going to have to do here is come over here with a little section and make a little cut, and I'm cutting the y-axis, so here's my little delta y. And how much rope do we actually have? Well, this is a little delta section of rope, and that thing, what does it weigh? It weighs 0.1 pounds per foot, and you've got delta y, a very small section measured in feet of actual rope. So delta force is equal to that 0.1 pounds per foot times your delta y feet. Notice your feet cancel. This is measured a force. Your force is 0.1 delta y. So your work on your rope is going to be the sum of 0.1 times delta y times where you got to lift this thing. Now here's the deal. I could have made the cut up here, down here, anywhere. Officially, I'm making all these little cuts, and then I'm going to sum them all up. That's what you're doing. But we're only analyzing one little cut. And this cut was made at an arbitrary y level. What is the distance? I got to take that arbitrary delta y little section of rope. Well, how far do I have to lift it? I got to lift it to my target, which is 20 feet. So what's the distance I have to lift? Very good. 20 minus y. Top minus bottom. The 20 is the target. Y is the arbitrary level I made my cut. It's 20 minus y. Notice I'm doing the same thing over and over and over again. I'm setting you guys up. Does that make sense? Now set up my integral here. Work on the rope would be equal to summation turns into integration. 0.1 is a constant times 20 minus y, and the delta y turns into dy. And all I need to now is figure out what my bounds are. What are my bounds? Well, this time we're trying to lift the entire bucket off the bottom to the top of the building here. So what's my bounds? 0 to 20. And just to save a little time, because this is easy integration math, I'm just going to put that on the old calculator here. This would be 0.1 times math number 9, function integrate from 0 to 20 of 20 minus y, or in this case x dx. And I get 20. And what would that end up being? 20 what? Foot-pounds. So what is the work total for this particular problem? What's my answer going to be? Well, it's the work on the bucket, which was 40 foot-pounds, plus the work on the rope, which was 20 foot-pounds. So the work total would be 60 foot-pounds. Did I lose you guys anywhere? Does that make sense? But watch what happens when you look at it from a part B, part C perspective here. So here's part B. What did part B ask you guys to do? It asked you to, quote, find how much work is needed to lift the bucket and the rope from the ground halfway up the building. And they're focusing on it 0 to 10. All right? So now, here's my, my bucket. And here's my rope up here to the mark of 20, okay? And we got the guy lifting it up here. But we only want to cut it halfway, from 0 up to 10. We want to lift this part here. So, again, you've still got a rope and you've still got a bucket. So you're still going to have to do one of these work totals, which is the work on the rope plus the work on the bucket. The work on the bucket is very simple because it's a straight lift concept. The force on the bucket was 2 pounds times, what was the distance we have to lift the bucket? We're going to lift it halfway up, and how far is that? 10 feet. So this is 10 times, 2 times 10, which is 20 foot-pounds. Does that make sense? But look at it from a calculus perspective on the rope. Work on the rope is that sum of the delta force times distance that you got to lift. So in the delta force, we're coming over here, I'm going to make a little delta y slice because this is the part I'm removing. This rope still weighs 0.1 pounds per foot, and I got a delta y feet of rope here. So delta force is equal to 0.1 times delta y. So work would be on the rope would be the sum of 0.1 times delta y times the distance I'm going to lift. This is still an arbitrary distance, and where are you lifting it to? Well, I'm trying to take that section of rope and we're trying to lift it where he's at, which is still the top of the building. Does that make sense? We're trying to lift it, we're just going to stop halfway, but the ultimate goal is to get it to the top of the building, which is at 20. So what's that distance I have to lift? 20 minus y. When you convert it to integral calculus, work on the rope would be 0.1 times integral of 20 minus y, and the delta y turns into the dy. The only difference is, what are my bounds? What's the part I'm removing? I'm removing this section of rope up here, so I'm integrating it from 0 to 10. Again, just to save some time, I will use my calculator, but notice, it's the exact same problem as what I did before, except my bounds have changed. But watch what happens when I change my bounds. It just doesn't split that, 20 foot-pounds in half, it becomes 10 foot-pounds. It actually does a little more. Let's take a look. What do I get? I got 15 foot-pounds. My question to you is this. Why is it more than half? Well, okay, in that concept, I agree with you. There's more rope because it's the distance. The distance that you actually have to cover, there's still more rope that's still being there. So you've got more weight to actually be able to handle. Does that make sense? More rope, so there's more weight on that rope And so it actually is, because that force on this section of rope is going to be more than the force on this section of rope. Does that make sense? Because I'm trying to lift this thing just 10 feet, granted, but my target's way up here, and I got all this other rope that I have to consider that's going to be part of my weight in terms of trying to lift this rope. That is why. And so for part B, the work total would be the work on the rope plus the work on the bucket. But the work on the rope, this one is going to be 15 plus the work on the bucket, which is 20. And so what does that equal to? 35 foot-pounds. Well then, what is part C? Part C is how much work is needed to lift the bucket and the rope the rest of the way? Well, the rest of the way, well, the whole answer was 60. If I just go for the first section from 0 to 10 was 35, what do you think the last one's going to be? 25 foot-pounds. And that would be actually correct, but I want to show you the math. Again, the work total for part C would be the work on the bucket plus the work on the rope. The work on the bucket is still going to be force times distance. That force was 2 pounds. Then we're going to lift it the rest of the way, which is another 10 feet. That's 20 foot-pounds. That's correct. But then you've got the work on the rope. The work on the rope is the sum of that delta force times the distance that you're going to lift. That'll be the sum of the same, it's 0.1 delta y, same delta force. The distance we're going to lift is the same as 20 minus y. And then converting it over, this will be 0.1 times integral of 20 minus y dy. But my bounds are different. What's my bounds now? 10 to 20. I'm going to, quote, lift it the rest of the way from 10 to 20. And when I put that on my calculator, you're going to see the difference. Integrating it from 10 to 20 actually changes it significantly and makes it 5 foot-pounds. And so when you put your two answers together for the work total, that's the work on the bucket plus the work on the rope, that'll be 20 plus 5, which makes it what you told me it was going to be, 25 foot-pounds. And what you need to focus on is the distance you're trying to do the lift away from the target of what you're trying to get it to. The distance I'm trying to lift when the target is actually officially the top of the building, the work on the bottom section is going to be a lot more than the work on the top section because of that. Well, you've got it almost to the top. Your rope is actually weighing a lot less by this point. Does that make sense? Questions? So check out these patterns. But what I'm doing is I'm setting up the same integral each time. Well, the next kind of problem is called springs. Now, things you guys need to know about springs. And again, we are bringing up a lot of physics stuff in here because this is a physics problem. But if you've never had physics before, don't worry, we'll give you the formula. But most of you guys at this point should have had physics before, whether you've gotten Physics 1 under your belt or currently taking it right now, or you took physics in high school, you should have had some kind of physics background, some type. If you haven't, it's okay. We're going to give you the formula you need to know. But majority in a Calc 2 type of class, usually you, by whatever your major is, requires you to already have physics at some point here. So, when it comes to springs, what do you guys know about springs? Well, there's different kinds of springs out there. They compress and expand and stuff like that. And what you should really know is something called Hooke's law. If you've got to have a spring right here, okay? Now, what we're talking about here is something called the natural length. The natural length of a spring is the distance a spring is at rest. Distance a spring is at rest, okay? So you're not moving this thing at all. First off, this will be your measuring point. This will be your zero. Listen, you're going to have to calibrate your spring system. This is calibrating your spring system. This is going to be your zero mark right here, because this is where you start measuring. That's the first thing. The other thing you need to know about springs is something called Hooke's law. Hooke's law states this. A force exerted on any spring is proportional to the distance you have to compress or expand the spring. Proportional to means is equal to some kind of spring constant K times the distance that you actually stretch the spring. X is the distance we're going to stretch the spring. Okay? Now, let's talk about physics and what you guys already know. Now, if I open my really cool pen here and open it up, and let's see if I don't shoot this thing across the room here. Pull off my little bullet top here. There's a spring right here. You with me? Now, this is my classic spring. If I take this spring, this is the natural length of the spring, which is about, what, 2 inches or 1.75 inches or something like that. That's what I got. Okay? It will not, and it doesn't take much force at all. It just takes balance. Oh God. I'll get it later. All right. Luckily, I came up with another pen. That's why I always carry two. So, all right. So, but if you notice, when I stretch the spring, I really don't want to lose that spring. There it is. When you stretch the spring, again, not shooting it across the room, it actually doesn't take much force to exert on the spring to actually just compress it just a little bit. So this will be a very small spring constant. Small force is equal to some spring constant times the distance that I stretch it. Small stretching. Does that make sense? So it's a small amount. So this is going to be a, quote, small spring constant. Now, give me another spring. Have you guys ever played with a spring on your shock absorber on your car, your shock springs? Now, those things are a pain to play with. Have you ever actually tried to put those things on your car and stuff like that, or just take a little thing, it's in the housing, but if you ever tried to kind of push it together or whatever, it takes an incredible amount of force because those springs, they are actually got a diameter about like this and they've been coiled, right? So it takes a large amount of force just to compress that thing just a little bit. Because remember, what's the goal of a shock absorber in your car is to give you that smooth ride. So you hit those awful potholes we got here in Charlotte. You hit one of those things, but your car still rides at a nice smooth rate because your tires are all over the place, but you don't feel it because the shocks are taking, that spring is taking all that hit. Does that make sense? But it takes a large amount of force just to move one of those springs a very small amount. That's going to be a very large spring constant. The other aspect of this thing is this. Work is equal to force times distance, right? Now, in terms of integral calculus, we did this. Work is also equal to, I'm going to use the other formula, the sum of force times your delta distance. This time I put the delta on the distance part. I'm using my other formula that I created for you guys because this is the one that's actually used for springs. When you write this out, another formula you're going to get is work is equal to summation turns into the integral of force, and your distance, x is going to be distance, and delta stands for d, dx from A to B. This is another formula in your repertoire of formulas you need to know. Another way of looking at force is always equal to the integral of, work. Work is always equal to the integral of force dx. That's a formula. Work is always equal to the integral of force. So if I ever give you a force function, you integrate it dx from whatever a and b I tell you about, okay, over your bounds. But thanks to Hooke's law, since force is equal to k times x, and again, k is arbitrary. K is going to change based upon the kind of spring you got. Whether you got a spring out of your pen or you got a spring off your shock absorber, that K is going to change based upon if it's a very heavy spring or a very light spring. So you're going to have to figure out what that spring constant is, but it is a constant. So work is equal to the integral from A to B of Kx dx. This is the actual formula for actually calculating work when it comes to springs. I'm using Hooke's law, and I'm just integrating Hooke's law. Integral of force, dx, which is the integral from A to B of Kx dx, Kx being the Hooke's law formula, where K is called the spring constant. So, again, the other thing that I mentioned to you guys on this kind of problem is the natural length. A spring has a natural length. When you saw the spring that I pulled out of my pen, It just sat there. It wasn't bouncing and moving around until I actually tried to compress it and shoot it across the room. It was just sitting there. The natural length, called equilibrium, a spring at equilibrium where it's just at rest, is called the natural length, and that's where you start measuring from. So let's take a look at this first problem right here. Okay? Now the other thing is, down here in terms of my type, the other thing, again, I want to focus on units. Now when it comes to units, remember, work is measured in the metric system, joules, in the English system, foot-pounds. So in the English system, it's foot-pounds. But if you notice that I had that spring right here, which is about yay long, I'm not going to be stretching it any kind of feet. Does that make sense? It doesn't make sense because it's a very small spring. Typically, I would stretch this thing out in maybe inches or fractions of inches. But again, I still want my answers in terms of foot-pounds. So you're going to have to convert. So let me tell you, how many inches are in a foot? 12. So if I've got 12 inches of something or other, I got a 1 inch that I compressed the spring out, I got to divide that by 12 to convert it to feet. You're going to have to convert your units. Same idea with the metric system. In the metric system, we're talking about the joule, also known as the Newton meter, right? So meters is going to be your standard unit of length, but typically if I got something small or something big, play with that shock absorber. Go press that thing a meter on your car. You'll never make it, okay? You're going to be measuring those things in centimeters or millimeters as best you can be able to compress these guys. So based upon that, you're going to have to convert. So if I've got centimeters, centa means there's 100 centimeters in a meter, I divide by 100. If it's a millimeter, if I got 5 millimeters in terms of turning it into meters, milli means there's 1,000 of these guys, so I got to divide by 1,000. So make sure you know your units and how to convert this stuff over. So now, here we go. Typically, when it comes to spring problems, there's two types. And I'll describe those two types in just a second here and what the difference between the two is. But this is what I'm going to be calling type 1. Now let's take a look at the question here. It says this. A force of 40 newtons is required to hold a spring that has been stretched from a length from its natural position of 10 centimeters to 15 centimeters. The question is, how much work is done in stretching a spring from 15 centimeters to 18 centimeters? All right, so we got ourselves a spring. So I kind of drew you a picture here. Here's a spring. Now the first thing you need to know is this, natural length. This guy's my natural length right here. I'll call him NL, natural length. My natural length of the spring was what? 10 centimeters. So this is my 10 centimeter mark. So from this point to the wall, that's 10 centimeters. So natural length. But what they told me was it took a force of 40 newtons to go from the natural length of 10 centimeters to 15 centimeters. To go over here to 15 centimeters, if this is 10, this is 15 centimeters, it took, and here's the most important thing, a force of how much? 40 newtons to actually stretch the spring out. Does that make sense? So I had to yank this spring and pull on it and stretch it out from 10 centimeters natural length to 15 centimeters. The question, of course, is how much work is done. So we're interested in work. How much work is done in stretching from this point of 15 centimeters to 18 centimeters. Does that make sense? Now, first things first. Here's the deal. Your natural length is your equilibrium point, and that's really where you first start measuring from, and you got to zero out or calibrate your system. So the natural length, which was 10 centimeters, this is going to be my 0 centimeter, because that natural length should always be 0. Because if you don't do that, your problem will never come out right. That's got to be your 0 mark. But let's do the math. If 10 centimeters is equivalent to 0, because that's where the natural length or the equilibrium of the spring is, what does that make 15 centimeters? How far did we actually stretch the darn thing? 5 centimeters. Does that make sense? And while we're at it, if you're talking about 10 centimeters is equivalent to 0 centimeters, what does that make 18 centimeters really equivalent to? You actually stretch it out 8 centimeters. But you got a problem. Look at your units. They're in centimeters. That's bad. Because we're in the metric system, the standard unit of length is the meter. So we got to convert. What exactly is 0 centimeters? No problem. That's 0 meters. What exactly is 5 centimeters? Convert that to a meter. Centa, you divide by 100. That would be 5 divided by 100, or 0.05 meters. Does that make sense? And 8 centimeters would be equivalent to what in terms of meters? Divided by 100, 0.08 meters. Now, the question is, of course, how much work? Work is equal to the integral of kx dx from A to B. In any, listen up, this works for any spring problem we give you. After you analyze the given information, the first thing you've got to do is figure out what K is. K sets the stage of what your spring is. What is K? The first piece of the puzzle that they always give you is just enough information to figure out what K is. What's K in this problem? So, they gave me 40 newtons. Look at that, newtons, that's force, to go from your natural length of 0 meters to 0.05 meters. I have a formula for a force in springs. Force is equal to Kx. You see where I'm going. The force is 40 is equal to K times the distance from its natural length. I stretch it out, was 0.05. So what have I got to do to solve for K? It's an equation. Divide by 0.05 on both sides, and I get K to be equal to 40 divided by 0.05, and I'll stick that on the old handy dandy calculator here. 40 divided by 0.05 is 800. K is equal to 800, and if you wanted the units, it's force divided by distance. Force would be measured in newtons divided by the distance, which will be measured in meters. It's 800 newtons per meter. Does that make sense? But once you got K, you've got the problem done, almost. Work is equal to the integral of K, which is 800 x dx. All I got to do is figure out my bounds. Then we wanted to find the work in stretching a spring from 15 centimeters to 18 centimeters. But after you zero out the natural length and convert it to meters, that's going from 0.05 meters to 0.08 meters. Does that make sense? And those are my bounds, 0.05 to 0.08. Now, this kind of a problem, I'll admit to you guys that if you have to use your calculator to integrate this thing, you should be ashamed of yourself. Now, I use calculators a lot to actually expedite time and stuff like that, and I'll use some calculator problems to set up the integral and those volume problems that you guys have to do and stuff like that, just to, again, for time efficiency for the most part. But this problem, I can guarantee you on the test, I'm going to sit there and tell you, integrate by hand and show your work. So, integrate by hand and show my work. So 800 is a constant, leave it alone. Integral x with respect to x is going to be x squared divided by 2. Evaluated from 0.05 to 0.08. Now 2 goes into 800 400 times. That's 400x squared from 0.05 to 0.08. So this is equal to 400 times 0.08 squared minus 400 times 0.05 squared. And I'm going to stick that on the calculator. That's 400 times 0.08 squared minus 0.05 squared. And double check me, but I got 1.56. Now, you and I both know these are physics problems. You don't tell me units, you don't get credit. So, what are the units for this particular problem? You got, well, 3 options, but really 2 options. Is this the English system or is this the metric system? This is metric. We're talking about newtons and meters and all those other stuff. So what would my units be for the metric system? I would accept Newton meters, but honestly, joules is the preferred way of doing it these days. So 1.56 joules. Does that make sense? Now, before we get started on this problem, take a look at it. I call this problem a type 1 problem. There's only 2 types. It's about finding that K. This was the easiest type. I gave you force and I asked about work. Force equals F equals Kx, and I use that force to be able to figure out what K is. Look at the next problem. This is the type 2 of these type of problems, is this. Type 2 is, I'm going to give you work and ask about work. You go, wait a minute. So look at it. I give you 7 joules of work is required to stretch a spring from its natural length of 20 centimeters to 50 centimeters. This one I did a part A, part B. How much work is done in stretching a spring from 25 centimeters to 35 centimeters? And how far beyond its natural length will the force of 25 newtons hold the spring? So I got a couple of different questions here, but the first part is always the setup about how to figure out what K is. What did I give you in this one? The first part, 7 joules of work is required to stretch a spring from its natural length of 20 centimeters to 50 centimeters. I got a lot of unit conversion stuff here, but the last problem, I gave you force and you used it to find K. This one, I'm giving you work and you've got to use it to find K. 7 joules of work. So remember, force is equal to Kx, but work is equal to the integral of Kx dx. So if I give you A and B here from A to B, I give you A and B and I give you the work, you can integrate. K is a constant, it comes out front. Integral of x is x squared over 2. You can still use this thing and solve for K. Does that make sense? And then once you got K, then you can go and answer the questions. We'll do that problem next time. Don't forget, you will have for homework is due on Wednesday. Your calculator project is due. And we will finish up this and start pumping problems next time. Class you can't afford to miss. So I'll see you guys then.